So this is going to be kind of different. Our class time has been pre-recorded. As you're watching this, I'm recovering from a complete knee replacement, and I'm hoping that it won't take me too long to be back with you during class live. But we'll just see how this goes. And I will have announcements for you as to how you can get office hours covered while I am probably on pain medicine and you wouldn't want my answers. So after today's class, what you should be able to do with sapling, of course, is number 12 and number 13. These will finish up our chapter on solutions. And we're dealing with the colligative properties here. So you've watched all the lessons dealing with colligative properties, and I want us to spend class time practicing some problems. To get ready for your next class, due at midnight, is the sets of videos where we're entering our next chapter. Our next chapter is dealing with chemical kinetics. So this is the speeds at which reactions take place. And it's a completely different topic. So that is where we will be heading next. As a reminder, this is found in your interactive general chemistry textbook in sections 14.1 and 14.2. So we're going to introduce you to how to determine how fast a reaction is taking place. So let's just jump in with you speaking out loud. Now you're probably in a room by yourself and you can do this, but what I have found is when we speak things out loud, it is a different dynamic than if we just think them in our head. So you're out there, you're being I have it as a choir because when I'm doing it class time, I want everybody to say it together as a choir, but I guess this is going to be your solo. So what you're thinking about is, what is the next word of the colligative property? It is, and you're going to say it with me, vapor pressure lowering. Okay, now let's pause for just a minute. You're going to put the word, actually let's see if I can write on my screen here. I haven't done this in a while. Lowering. Okay. What I want you to do now is I want you to find in your notes where we did a similar thing with me within your lecture. It's vapor pressure lowering. You're saying that out loud, okay? Now, what does that mean? If you can remember the words vapor pressure lowering, it means that as the pressure goes, as the pressure will go, and lowering means down, okay? The pressure is going to go down, and that's vapor pressure. It's going to go down as the concentration goes up. So all of these colligative properties are how they are affected by putting more and more solute into the solvent. The next one was freezing. Well, let me stop it a second. You're going to say it with me, okay? So get ready to say it out loud no matter how silly you feel. I'm saying it out loud, right? It is freezing point depression, okay? So I'll write depression in there, and you have that, of course, in your notes somewhere, I'm thinking. But depression, freezing point depression, means again that the freezing point, the temperature at which it freezes, that's T sub F, goes, again, depression means down, okay? So it's going to go down as concentration goes up. I don't know why they didn't call it freezing point lowering also, but it doesn't roll off the tongue because I'm not used to it that way. It is always reported as freezing point depression, which means that you put more and more solute in, the freezing point is going to go down. All right, let's try our next one. Say it out loud, no matter how silly you feel. It is boiling point elevation, okay? Elevation. And what does that mean? Well, if it's boiling point elevation, that means that the boiling point, the temperature at which it boils, is going to go up as concentration goes up. Now that is the three colligative properties that have a qualifier associated with their name. Vapor pressure, say it with me, vapor pressure lowering, freezing point depression, boiling point elevation. So that helps you know which way it's going to go. It's very specifically important to think about which way it goes so that you can check your response when it's all said and done. Did your vapor pressure go down? Did your freezing point go down? Did your boiling point go up as you added that solute? Okay, so that's just something you probably ought to say over and over again so that you get familiar with the language. But we're going to have you just write this problem down, okay? This is a problem that's very similar to one that we worked through together in our lecture. But I've changed some numbers, some substances, but the concept is the same. So you're writing it down. What is the osmotic pressure of a solution that contains 1.27 grams of sodium hydroxide that's dissolved in enough water to make 250 milliliters of solution? So you can pause this and get that written down, and then also turn to your notes to see where we have done a similar problem in your notes. And I'm going to guide you through this process. I'm not going to just say, work on it and get an answer. Now you can ignore everything that I'm doing if you want to. So you can pause and say, let's see if I can follow my notes and get to an answer. But if you're sitting there scratching your head and you're saying, not sure what to do, let's just walk our way through it. Okay? So we're back together. I'm giving you two options. You can either stop me here, just stop it and see if you can, using your example in your notes, come up with an answer. If you find that you're struggling, then you will rejoin me, and I've got a lot of multiple choice questions for you to consider, all right, that are all of the thought process that I do when I'm working this problem. We're just making note of it, okay? So we're going to walk through them one at a time. All right. When we are doing an osmotic pressure problem, we know that we have that little I, that Van't Hoff factor that we have to consider. So the first thing that you want to do is pause and think, what is the Van't Hoff factor of the solute? Well, hopefully you chose the Van't Hoff factor being C, okay? Why is it C? Well, you have to consider what the substance is. It's sodium hydroxide. And sodium hydroxide is an ionic compound that breaks apart into sodium cations and hydroxide anions, okay? So that was something that we had to know. Why did we have to know that? Well, we had to know that because of the osmotic pressure equation. So I'll turn my attention back to the whiteboard here, and I will write on the board our osmotic pressure equation. Pi, or where is it? There it is. Pi equals, and somebody told me this clever way of remembering it, trim, okay? I didn't write it that way initially, but I like the rearrangement of the letters because you trim your pie crust, right? So we're trying to figure out the osmotic pressure. That's this capital Pi here. We need all those other things. So we saw that we need the Van't Hoff factor, and we have determined that it is a, and we can't see that, I'll write it underneath. We have determined that it is a 2. All right, so we need this equation. We're trying to find osmotic pressure. So here's the next question. When you're calculating the osmotic pressure, which concentration do we have to use? We have to know what these symbols stand for, and there's lots of choices here, so pick the right one. And with all of these, you pause, you think about it. I'm not going to do the pause that would happen in class time, okay? So this capital M is what we have here, and that is molarity. So you should have chosen A for that. So we've got our molarity. All right, let's go ahead and calculate the molarity. Now, where it says raise your hand when you have an answer, don't raise your hand. I'm not going to see your hand up. So I want you to pause and I want you to calculate the molarity. When you've got it calculated, you can resume and you can see what my answer is, or you can watch my work, just depending on which way you want to go. All right, so capital M, molarity. We know that that is moles of solute, for in this case it's sodium hydroxide, over liter of solution. Okay, so we need those two things. Well, I see in the problem that we have not been given the moles of sodium hydroxide, but we have been given the grams of sodium hydroxide. So that's 1.27 grams of NaOH. But we're going to go ahead and convert it right here from grams of sodium hydroxide to moles of sodium hydroxide. So this is the work of our numerator, right? That's the numerator. What is the molar mass of sodium hydroxide? So we have to go look it up, and I happen to use this one a lot, so I know it's 40 grams per mole. So I have my numerator there. And I want to know what, let's see, the denominator is. It needs to be liters of solution. All right, so if it's 250 milliliters, that's 0.250 liters. Now, by now, you're probably used to just moving your decimal point over, but remember, 250 milliliters. We don't want milliliters, we want liters. Milli means 10 to the minus 3. Some of you may say it takes 1,000 milliliters to equal a liter, and that's fine. And that will give me the 0.250 liters. Okay, so let's get a value then for this capital M, okay? And that is, I have calculated it here, a 0.127, 0.127, that's moles per liter. All right, so there is the value. Hopefully, when you paused, that's what you got. And if you did not get that, you can always look at my work. If you did get that, you can advance your slide in every case. Okay, so we have another thing in this equation, and that is R. R is our ideal gas constant. For our ideal gas constant, we have some choices here. Which one would we use? Well, we have to use the one that has the pressure unit in it, because osmotic pressure, okay, we need to have a pressure unit, and that would be A. So the right answer for that is to make sure that we have A there. And the next question, all right, we've got a temperature here. Temperature can sometimes be in all sorts of different units. For this equation, what must you have the unit of temperature in? Well, I hope you picked C. C it is. All right, let's back up just a minute. Look at the value of R there that you see in A. That's our reminder of what temperature needs to be in. You see that big K? It has to be in Kelvin. Anytime we're working with gases, we're always dealing with temperatures in Kelvin. This is not a gas, okay? I don't want you to think it is. But it is derived in a similar way as PV equals nRT was derived, okay? It is using that same gas constant. We've got to make sure we have our temperature in Kelvin. All right, so we've got a few things here we need to consider. All right, so then you're going to go ahead and calculate it. Let me just write a few things around here, right? We've got pi equals a temperature. Temperature has to be in Kelvin. 25 degrees Celsius plus 273 is going to give you 298 Kelvin. Okay, so I have 298 Kelvin. You can pause and you can work it yourself, or you can just follow with me. Okay, I think what I'll do is I'll just be quiet and work, and you be quiet and work, and then you can look up at the work I'm doing and see if they match. All right, so I've got 6.21 atmospheres. Let's just look at our units. Notice the kelvins are canceling, okay? The moles are canceling, the liters are canceling. We indeed are being left with atmospheres, and that's what pops out for us when we use an osmotic pressure equation. Now, for that equation, just want to remind you, you should be able to solve for any one of those variables. But all you're doing is looking through and you're logically well, not logically, you're just thinking about the units for each one that you must use. And if you will remember the units of R, that will help play out the units of everything else for you. All right, I believe we'll stop with this problem, and you can rejoin me with the next video for another example problem.